Okay, this is exciting. We reminded ourselves of gradient ascent and what that looks like. We figured out what the logistic regression model is. We talked about maximum likelihood functions and estimation, and we explored quite a bit of that math. Now let's dive in and look at the actual learning algorithm for logistic regression. That learning algorithm is going to be extremely simple. And so, despite all the math we've seen, we'll come up with an algorithm that you could implement in just a couple lines of code. To define a gradient ascent algorithm for logistic regression, all we have to do is define the derivative with respect to each parameter wj. So what's the derivative for likelihood function with respect to wj? By the way, these derivatives, side note, are going to be of the log of the likelihood function, the log likelihood, and I'll explain a little bit more why that is in an advanced section of this module later on, an optional one. But just think about it as a derivative of the likelihood for now. Now, that derivative of the likelihood is going to be equal to the sum over the data points. So we're going to consider each data point has a contribution to the derivative. Some when they want to make wj big, some want to make wj smaller. But we're going to sum over the data points of the difference between the what's called the indicator function that the data point is +1. So indicator of whether this data point is positive. So I'm going to specify it at the bottom here. So let's get our ink. So this indicator function, it simply says output 1 if yi is truly a positive example, and output 0 if yi is a negative example. So that's the indicator is. So this is this definition over here. So is this a positive example? And the second term, so it's the difference between that and whatever my model predicts, how much my model does far predict that xi is positive. In other words, if this is the difference between the truth, is this a positive example, and the likelihood that my model assigns to being a positive example. And we're going to weigh it by the feature value xj. So this, for example, is the number of awesomes. So if a data point has many, many awesomes, then it has more contribution to the derivative because that coefficient is going to be multiplied by, say, 20 awesomes. If it has 0 awesomes, then there's no contribution here because whether the coefficient is high or low, it doesn't make any difference to this data point. So that's why we weigh it that way. So this is exactly the derivative that's very simple that we're going to implement.